Around 2.4 to 2.0 billion years ago, life on Earth experienced a monumental transformation, known as the Great Oxygenation Event. Before this period, the Earth's atmosphere had almost no free oxygen. Instead, early life forms, mostly single-celled prokaryotes, like archaea and anaerobic bacteria, relied on anaerobic respiration, using molecules like sulfur, methane, and iron as electron acceptors to extract energy from food. These primitive microbes lived in a reducing atmosphere, rich in methane, ammonia, hydrogen, and carbon dioxide. Oxygen, if present at all, was in trace amounts and highly toxic to early life. Things began to change with the evolution of cyanobacteria, microorganisms capable of oxygenic photosynthesis. These microbes used sunlight to convert water and carbon dioxide into glucose and released oxygen as a byproduct. At first, the oxygen they produced was absorbed by dissolved iron in the oceans, forming banded iron formations. But over time, as iron became saturated, oxygen began accumulating in the atmosphere. This rise in atmospheric oxygen gradually altered the planet's chemistry, making it increasingly hostile to anaerobes, but opening the door for a new kind of metabolism, aerobic respiration. Aerobic respiration, using oxygen to produce energy, is far more efficient, yielding up to 18 times more ATP per glucose molecule than anaerobic pathways. This metabolic leap gave aerobic organisms a huge advantage, allowing for larger, more complex life forms to evolve. So, to summarize, before the shift, anaerobic respiration in a low oxygen, methane-rich atmosphere trigger evolution of oxygen-producing cyanobacteria. After the shift, rise of aerobic respiration and the oxygen-rich atmosphere we have today. This was not an overnight event. It took hundreds of millions of years, but it permanently reshaped life on Earth.